I'm very privileged to join this symposium here. I've known this man for 40-some years. You have to echo a lot of what Jeff Post was saying earlier, because I showed up, about, I don't know, 6 years after he did. I met him once at the door when he came looking for you in the summer when you were at Los Alamos. But I have a few comments here. I mean, there's so many things that have happened during the year. Of course, some of this is lost in antiquity, which is a real problem. If I had a little bit more time, I could have dug through the shoe boxes to find some of these pictures. But I'm thinking that way back when, we started working on the X-ray line shape fitting for profiles with data from Arizona State with rutile and anatase, and that worked pretty well. And then I think it was sort of the beginning of using X-ray fitting for, or X-ray data for GSATs. I remember taking the samples of lithium tetrahedrite to Oregon to collect data, and it was, you guys just wouldn't believe how this works. So, I mean, we had time on a GPPD, and Bob came up with this brilliant idea. He told me to go ahead and just put all this quartz wool inside the sample in order to break up the large single crystals we would end up with. We did. I mean, we couldn't see them because of this big mass, but he had the bright idea of just going ahead and rotating this crystal 5 degrees at a time while we were doing our acquisition of data, and we got a usable product out of it, and we published that. And we also worked on these various intercalates of dichalogenides, oh yikes. And of course, my first exposure to Bob was working in the X-ray diffraction course, taking that from him. Yikes. It was so long ago now, 42 years ago. But we got through that. We solved our own crystal structure. We learned a lot from it. Just as Jeff was saying, we go ahead and get these Fourier maps. You go ahead and get your pencil out and find your atom positions. Do a Patterson solution, put the atoms in, life is good. It took longer than it does now. But the course that really made a difference for me was the neutron diffraction and scattering course that he offered 2 years later, or what? Something. Yeah, it was a year after that, I think. And I'll tell you, I learned so much about neutron scattering and diffraction and how it's applied and the various physical conditions. And that's benefited me through my entire career. Oh, yikes. And of course, my major prof, Bob Sander, left in the 4th year. I was sort of left, I don't know, high and dry. And Bob sort of took me in, and I finished my PhD under Bob. One thing I've gathered about crystallography, because I've been a practitioner all these years. I work at the University of Minnesota. I'm 29th year now. Lifelong learning is very important. You never stop learning what you do. Let's see what else is the last one. And of course, recently, Bob and I have collaborated on a few other things, which are upgrades to the GSAS codes. A couple years ago, we went ahead and I supplied all the twin data sets for him so he could test. And so in GSAS now, you're able to go ahead and do all the various types of simple twinning. Recently, I provided him a modulated data set and then also charge density. How the charge density down?
I'm still working on it.
Yeah, I imagine. Yeah. Yeah, well, I know we might have to work on that again. I mean, that was first crack at that. So anyways, today I'm going to be talking about twinning in the CSD. I'm showing current work. I didn't have enough chance to dig through my archives to find stuff. So, but there we go. So a few years ago, Bruce Foxman and I started working on using the Cambridge database, trying to harvest data about twinning and learn about what people have done with twinning, looking for a few features in that. So, I mean, there's 1.2 million since 2023 of deposited structures, and there's a fair number that are cited as twins. The problem is that many of these are just not really twins, and so part of our job is to try to sort out ones that Shellix is sort of flagged as twins, and of course Shellix is the dominant program out there. But just because it says it's a twin, it doesn't mean it really is. So there's a bunch of them that need to be filtered out. Of course, you're talking about all these years of acquiring data in the Cambridge database. So the problem is that CIF deposition with data really started in the 90s. Well, before that, this data is just basically in papers, and you have to extract it by hand if you want to do that. We also started looking at Z prime and ZN and Z prime N were 1 or 2, and looking for these twins that also have pseudosymmetry in them. And we've been learning stuff about that. I'm going to show some of that. And I sort of have an interest myself in looking at the composition planes of these various twins and trying to learn a little bit more about what's going on in them. So what we're doing here is we have a procedure. Of course, Bob remembers the program crystals. Probably has a love-hate relationship with it. But this is what we used at Arizona State way back in the dark ages, and it worked. It was a good product for that time. But David Watkin, of course, has continued to make this program continually relevant. So we have this tool in here called Match, and in Match we'll go ahead and look for another molecule that's in there. You can define it. So if you got a Z prime equal 2, it'll do an analysis for you and will give you the pseudosymmetry of that. So we're able to take a look at its twin law and maybe understand a little bit more about what's going on with that particular material. And Bruce has also made a couple of ancillary programs to look at data and look at the structure and try to understand what we have for these twin relationships. So ultimately, for many of these, we're looking at pseudosymmetry matrices, and then we're looking at twin laws. The rotational part of the twin law very often matches the pseudosymmetry matrix. If that's the case, then we end up having a possibility that we have a low temperature crystal form that was at room temperature where the crystals were grown was never actually modeled. So, or characterized. So here's a cartoon to sort of explain what I'm talking about. Many of you are familiar with looking at P21 like this. So we have two molecules in here. One's up a half, one's up at plus. If we go ahead and rotate this 90 degrees here and look at it side on, two-fold screw this way, we have two molecules like this, one plus, one minus. So, I mean, this is just P2 sub 1. But if you have a phase transition from P2 sub 1 to P1, then you end up having a twin has to form here because it's going from higher crystal symmetry to lower crystal symmetry. That symmetry that's lost has to go into the twin law. So what this is going to illustrate here is that we have two twin individuals. We got the red one, we got the blue one, we got a composition plane between them. And what we have here is we have a gold and magenta Z prime equal 2 structure. Z prime equal 2 and Z prime, or Z equal 2. So the relationship between this and this here is going to be a pseudosymmetry. The relationship between this one and this one here, which are gold, because of the twin law here, that's going to be the twin law. So what it turns out is that this can be used as a test to find out whether we could be at a possible low symmetry form of a crystal. So this is what we're using in part of our study. So match in crystals is implemented pretty easily. Basically what we do is we get a whole series of CIF files, dump them in here, and you'll do an evaluation on each one of these. And it gives you a lot of information. So this is just a summary, which is actually pretty useful, and I've highlighted a few things here. So for this CSD ref code BobFub, I guess, it has a transformation matrix like so. Basically, it's got a 1 bar in this position, 1 bar here, and an off-diagonal term. So this gives an idea of what's happening with this particular one. It's in P1 bar, no, P1. So this is the cell constants for that. This is the twin operation, and it matches with the pseudosymmetry matrix we have. So this is one of these twins that's in the Cambridge database, cited as a twin, and it looks like this could freely have a high temperature form that was never characterized. And so here's BobFub. There's a listing for it right in the Cambridge database. There's 2 complexes of this in there. It's got some solvent. It's a little bit messy to look at. So I'm crazy enough to actually try to look at the composition plane of this stuff. So that's where I'm going with this. If you use this tool in Mercury, which is really useful, you can see whether or not a mirror operation or just a rotation operation actually is useful for overlaying these. And none of these is really good here. It turns out that there's a ligand out here that's just not fitting very well. Probably it just turns out that it's got its own free rotation. This is my opportunity to try to make an overlay of this. So this is, I'm identifying the various parts of this. And we've got we've got 2 cerium complexes in here. We have a pentane molecule here, which is near a 2-fold axis. That would be in a higher symmetry form. We have a THF molecule here, 3, and then there's a second THF molecule that's buried in this that we can't see. But then you go ahead and do a rotation on this one, you set it on top of that one. We have a composition plane that makes sort of physical sense. All these molecules overlay in space, life is good. So this basically makes sense. That is a possible, there's a high temperature form for this that's not characterized.
How did you get CSD entry to be named after Bob?
I don't know. I paid a lot of money. I'll do one more of these to show you. This one's kind of cool here. So sometimes you can have a 2-fold operation. Sometimes you have a mirror operation. So part of what I'm trying to do in this is see if the twin law that was used for this is actually incorrect. If they used a rotation operation when they should have used a mirror operation, this is how I find it. So this is the molecule, it's a steroid. And if we go ahead and do an overlay, it's okay. It's not great, but it's not unreasonable. So the summary output for the CSD for Gerbig is this is the match transformation matrix. This is the twin law. It's pretty good between these two if you look at these numbers. And then from Foxman's omega-2 program here, it's got basically the same sort of law. But it turns out that this one here is going to have a inversion operation. It's going to have a mirror through here. So I'm interested in doing overlays of these molecules to see what the composition plan is. So right here, this is sort of how the thing fluxes into each other. In order to do this, you basically have to take a molecule, transform it by the pseudosymmetry operation that is in this, and it'd be a y plus a half. So the molecule is y plus a half, and then overlays, and a very nice fit in here. So this is a composition plane that actually sort of makes physical sense. And I think I'm going to skip this one and go on to this one. There's part of the problem we've had with the data that we got out of the Cambridge database is that it's incomplete. Sometimes we look for actual diffraction data and we don't get any. So sometimes there's not any diffraction data. It turns out that this one doesn't have any diffraction data. It's sort of useless. But it's got a nice model. We sort of suspect this one has a mirror operation, not a rotation operation. And there's nothing I can do about it because they won't give me the data. Conclusions: out of 21 structures in P1, 13 were observed to have a likely match between twin law and pseudosymmetry matrix, and 3 showing likely errors in choice of twin law. So about a quarter of them incorrect, possible mirrors instead of rotations for the twin law. In P1, CSD files regularly do not distinguish between inversion twins and true twins. No doubt we'll find this to be true for other non-central symmetric space groups. Many of the so-called twins in P1 are not inversion twins, but they have flag parameters. And this is just due to Shelley's. That's the way George coded it. If he suggests, well, you ought to refine your batch scale factor for twins. Well, if it has any number there, it shows it as a twin in the Cambridge database, and that's not true sometimes. Many reported twin laws of 4 structures look like they were incorrectly refined or reported. Found one that was reported as a twin, and it's actually a higher symmetry space group. Once a composition plane is formed, the user can now explore hydrogen bonds and non-bonded contacts between twin individuals. That's very useful for looking at the structure of these materials and how they hold themselves together. A couple of acknowledgments here. David Watkin, Richard Cooper for use of match in the crystals program. Some of the data you saw was supplied by Pat Carroll and Jeff Camp. We got an acknowledgement from my instrument at University of Minnesota, and productive discussions with CCDC on use of Mercury. Mercury's turned out to be a real good tool now, and we keep on evolving it. And this is for you, Bruce Foxman. Bob, all good wishes on your 80th. As a 1942 baby, I passed that milestone last year and can testify that crystallographic research is more fun than ever. Keep up that brilliant work and the best of health, and enjoy each and every discovery moment.